Alright, so let's take a moment and look at colligative properties. And the important thing to note that colligative properties are dependent on the number of particles, and really specifically solute particles, in the solution. The colligative properties that we're going to be looking at are freezing point, freezing point depression, and boiling point elevation. Okay. So what happens is these particles that go into the solution interfere with intermolecular forces, okay, and depress the freezing point, and then they elevate the boiling point. Right, we use delta TF. This is going to be the change in freezing point. Okay, so we're going to take the normal freezing point and we're going to subtract the delta TF to get the new freezing point of a substance. This delta TB, which is the change in the boiling point, we're going to find the new boiling point, new, by taking the boiling point for the normal or pure substance and adding the delta TB that we calculate. This I is equal to 1 for non-electrolytes. That is, molecular substances that stay together as a whole molecule when I put them into solution. The I is equal to the number of ions in a strong electrolyte. So for a totally soluble ionic salt like sodium chloride, I is going to be equal to 2. For something like calcium chloride, I would then be equal to 3. Because remember, when I put this in water, I'm going to get the calcium ion, and I'm going to get 2 chloride ions. The K's are constants that you have to look up, or you have to be provided with, and that M is the molality of the solute in the solution. So let's put this, see how we would apply this in a problem. So I want to calculate the freezing point of a solution containing 0.600 kilograms of CHCl3 chloroform and 42 grams of eucalyptol. And I'm given the formula for the eucalyptol. And to save us the trouble of looking up in the table that was in the Brown and LeMay, I'm given that the Kf for chloroform is 4.68 degrees Celsius per molality, and the freezing point is negative 63.5, and that should be just degrees C. All right, so what I want to do is I want to calculate the delta TF. And from before, I know that it is this formula. I don't like the orange color. So delta TF is equal to IKF times the molality. This is a molecular non-electrolyte, so my I is going to be equal to 1. I am given my Kf, so I have to calculate the molality. What's molality again? Well, molality is the moles of solute over the kilograms of solvent. Do I have enough to calculate the moles of the solute? Yes. Ooh, and I'm given just the kilograms of the solvent. So let's go ahead and do that. I have 42.0 grams of C10H18O over the 0.600 kilograms. So I will find a molar mass for C10H18O, and that will give me my molality of the C10H18 oxygen. So, let's see, 10 times 12.01 plus 18. I get a molar mass of 154.28. So I get a molality of 0.45372. So I think I have enough to calculate my delta TF. My I is 1. My KF is 4.68 degrees Celsius. Molality times my 0.45372 molality. That'll give me 2.123 degrees Celsius. I'm given the normal freezing point as 63.5 degrees Celsius. I'm going to subtract the 2.123 degrees Celsius because it is a freezing point depression, making that freezing point go even lower. And I get an answer of negative 65.6 degrees Celsius.